You should be host now, Raul.
Yes, I see that.
Well, how do we know how many has joined? Because the participants on the panelist are only 9, right? So people joining from the other links?
I can see one attendee that is not a panelist at the moment.
Okay, okay.
So can you see that, the attendees tab in the participant window?
In the right hand parts, okay, view. You're saying speaker, fellow host, attendee view. Okay, wonderful.
Right. So hopefully the number goes up quickly soon.
We can give a couple of minutes. Anyway, we have a 15-minute break. It's good to have more people listening to Gregg than have
Absolutely.
A couple of minutes lesser of a break. No problem.
Absolutely.
In Canada, it's already 11:30 in the night, right? The timings have changed.
Well, I'm in California now, but in Canada, I mean, in Montreal or the East Coast, it's 11:31. Yes.
Yeah, 11:31. So that may be the reason for a little lower.
Yeah. Well, some compromises had to be made.
Yeah. It's the problem of any international when you have so many time zones to be covered.
Right. Yeah. Right.
There are 3 additional people watching on YouTube, if that is any.
Okay.
Okay, Greg, I mean, the number doesn't seem to change. It seems to be a constant. So shall we start, Greg, Raul, or you want to wait for a couple of more minutes? I'm fine with both.
I will leave the decision up to Adelie, right?
I think we can get going, and then maybe more people will join as we go. If Greg is fine with that option.
That's fine with me.
Yeah, welcome, Greg. Please start off your first talk on space-based observations, an overview in a sense. Thank you very much. As I said, I'll give you a sort of a warning after 20 minutes.
Sounds good. Thank you very much. Okay, so yeah, my brief is to sort of provide an overview of prospects for space-based 21 centimeter experiments. We are very much still in the early days of those prospects. I mean, first of all, I want to review the obvious for most of the audience that will see this video, which is the reasons for going to space. And of course, the first and obvious one is to get above the ionosphere. And that's a benefit that benefits both experiments that are in Earth orbit and in lunar orbit or on the lunar far side. The Earth's ionosphere becomes opaque at around 30 meters or 10 megahertz. But of course, problems kick in a lot higher frequency than that. And it really is deleterious to a lot of the cosmological science that we attempt from the ground. And one way to avoid that is to get above the ionosphere. And really, for some of the key science, like the dark age cosmology science, you can do a 20 centimeter. It's the only way you're going to be able to do that cosmology. The other, of course, is the environment that you have with respect to the radio frequency interference. This is more specific to the lunar far side because you need isolation, significant isolation from the radio frequency interference from the Earth. And depending on frequency, there are other emissions as well too that are problematic. And we know that the lunar far side can provide something like 80 dB isolation from interference from the Earth in bands relevant for dark age science. And we don't just know that from simulations. We of course have data. This is an example of measurements from the Radio Astronomy Explorer 2 satellite in 1973, which actually measured directly the suppression of interference, both auroral kilometric radiation from Earth as well as RFI from Earth from the lunar far side. So we actually have had already experiments that have been in lunar orbit and took those measurements. Now, the notion of doing radio astronomy from Earth orbit, lunar orbit, or the lunar surface, the lunar far side, is not a new idea at all, and it's been around for decades. And that's the question: why hasn't it happened? As an example of how long it's been around as a notional concept, this is a snapshot image from a video I came across on YouTube a couple of years ago, and it's Arthur C. Clarke on the TV program Sky at Night on BBC in 1963, in which he makes a statement that on the far side of the moon, shielded from the electronic racket of the Earth by 2,000 miles of rock, there's an ideal site for radio astronomy. This is well before the Apollo mission was truly underway. So it's quite clearly it's an obvious thing to do. Although I will note that this is Arthur C. Clarke who thought of anything but obvious ideas. But the idea has been around for decades, and really now, though, I think in the last decade or so, the impetus has grown significantly because, of course, we have the motivation from 21 centimeter cosmology. And it is the fact that a lot of this cosmology is pushing down to the frequency domain where you're very much impacted by the ionosphere, that this is the motivation to go to space increases. And really, I think the key thing to point out is, obviously, you have the ionosphere becomes opaque around 10 megahertz at nighttime, maybe 25 megahertz in the daytime. But there are other effects that are caused by the fact you've got propagation through a turbulent plasma. And some of those effects scale as lambda squared, and some scale as lambda to the fourth power, which in combined means that moving above the atmosphere really does help, even at frequencies well above that 10 megahertz cutoff. And this motivation to go above the atmosphere and do dark ages cosmology using the 21 centimeter line was recently highlighted again from the Astro 2020 decadal survey, which called out as part of its 3 science cases in the new messenger and new physics science case that dark ages cosmology really is a frontier, and it is maybe the new frontier in cosmology. And it also highlighted as well too that specifically dark ages cosmology in the epochs earlier than 500 million years after the Big Bang is an area where there's an opportunity for discovery. Now, I will note while making that statement, there was no endorsement or mention of any space-based concepts to do that science, and that's definitely a mismatch because I don't see any other way to do this apart from doing 21st century cosmology from space. So it's clear that there's still some communication that needs to happen to the broader community to make it clear that to be able to do this science, we really need to be doing radio astronomy from space. Okay, it is worth noting that going to space does not solve all your problems. It is true that it does get you above the ionosphere. Depending on where you are relative to the Earth, it improves your RFI environment. And, you know, once again, depending where you are relative to the Earth, you do get thermal stability for extended periods of time, and your instrument is easier to characterize on longer timescales. There are disadvantages. Of course, in 21st century cosmology, we are typically systematic limited, and very often it's hard to understand those systematics, and we like to tinker and take data and tinker some more. That is not how it will happen when we build space-based experiments. It'll be one and done. We need to make sure we understand all of the systematics that we will encounter, and we need to understand the instrument incredibly well before we launch. And of course, a large collecting area is expensive. This is not an impact or a large impact for global signals, although even for the dark ages, it is a problem. For power spectrum measurements at high redshift, this becomes a huge issue. How you get enough collecting area above the Earth's atmosphere to be able to do power spectrum cosmology in the dark ages epoch. And then there are the same problems we have from the ground that transfer. You know, just because you have your antenna above the atmosphere does not mean you know its beam any better. So know thy beam is still, I think, a mantra that applies. And I think a mechanism to measure your beam from your space-based experiment is, I think, a key component that needs to be incorporated. And of course, you have to understand your foregrounds as well as you need to understand the foregrounds from the ground. So it's certainly not a change that solves all problems. With that being said, let's now talk about a few of the experiments that have launched or are planning to launch, and there really is now a growing increase in that focus. This is an example of one that is an experiment that is motivated to some degree by 21st century cosmology. It's an experiment that is associated with the Chang'e 4 lander. It's actually built onto the Chicha relay satellite, and it is a Netherlands-China low-frequency explorer. Essentially, it's a 3-antenna deployment that operates in the 80 kilohertz to 80 megahertz band. And these are actually snapshot images that show it pre and during and post-deployment. This is now an experiment at the L2 Lagrange point that is actually taking data. So it's an example of one of the first experiments to be actually taking data in the band rather than for the primary cosmology. In the US, a big impact, of course, is the fact that there's a strong push to return to the lunar surface. Artemis phase 1 is the first major step in that direction. And as part of that, you have the Commercial Lunar Payload Services Program, which involves partnership with commercial vendors to actually deliver payloads to the lunar surface frequently, as often as twice a year. And these are, beginning imminently, and offer opportunities for deployments of single antennas that can be used for cosmology. And here an example of some of those. This is an already approved CLIPS payload. This is called ROSE. This is the radio wave observation at the lunar surface of the photoelectron sheath. And this experiment's primary focus is looking at the photoelectron sheet density above the lunar surface, but it also has a lot of impact in our understanding of how an array deployed to the lunar surface for cosmology would actually be able to make those measurements. For example, characterizing multipath via the lunar subsurface, It will also measure the galactic spectrum below 20 megahertz. And this is a project being led by Robert McDowell, and I believe it's imminently due for launch, and it's using the Intuitive Machines Nova C as a means to launch. Similar concept is the Lucy Dapper payload. Lucy is a payload that involves characterizing the electromagnetic environment on the lunar surface. It's once again an eclipse lander, and the Dapper concept is actually a dark ages perimeter that will likely piggyback on the same eclipse lander. Now, Dapper in its original concept is a lunar orbiting concept, but for now the plan is to sort of bring those together and land in the Schrödinger Basin in 2025. Another very interesting concept that's a single antenna, but one with a lot more forward gain, is the LCRT, led from JPL. And this is a really amazing concept. It consists of a suspended receiver that's above a kilometer-sized mesh deployable antenna seated within a crater of about 3 to 5 kilometers. And this has been under development for a couple of years now. And it's currently entering NIAC phase 2. So it's actually a design that's already progressed to the first stage of NASA JPL development. And I think it's one of the concepts that has some of the best artist impressions of what it will look like. This is a beautiful image that shows what this will look like when fully deployed. But what about interferometry? Of course, those concepts I discussed are examples of ones that can make the first approach on a total power measurement of the dark ages. But what about measurements that involve interferometry? Well, the very first interferometers, radio interferometers, are actually planning for launch and gearing up for launch. Here's an example of one. This is SunRISE, the Sun Radio Interferometer Space Experiment. This involves 6 toaster-sized CubeSats in a flying formation that gives you about a 10-kilometer diameter in terms of aperture, operating between 0.1 and 20 megahertz with cross 5-meter dipoles. Essentially, these are stasers. And this is targeting an April 24 to September 25 launch date. So this is actually, pretty imminent, and the team involved are very active. And just to kind of be a sense of where they are, within the NASA project lifecycle and JPL in particular, they've gone recently through the phase B. So they really are converging now on that launch date. From my perspective, all of these mission concepts, any timeline is essentially aspirational until you see it on a plot like this, where it's gone through at least 2 stages of NASA or ESA or whichever space agency's assessment and planning process. Now, SunRISE is actually being designed for measuring and characterizing low-frequency radio emission associated with coronal mass ejections and solar energetic particle events, but it still provides, I think, the first basis for understanding how an Earth orbiting interferometer will operate and perform in Earth orbit. And I think is a major milestone and stepping stone to any future Earth orbiting or any sort of Earth orbiting or lunar orbiting concept for dark ages. These are just 2 animated GIFs to kind of highlight the concept from the solar side and how you have data transmitting down to the Earth, apparently by green lasers. Now there are additional, very large concepts extending all the way up to billion-dollar class concepts, and we're going to hear about, at least 2 of these in the coming talks. These include concepts from the US, China, India, and multiple from Europe. I'm going to focus on the first FarSight because I'm very involved with that project, but I will highlight that these are all concepts that are developing rapidly, and at some point there'll be an opportunity to maybe merge and bring these to fruition through a joint partnership. And we'll see how that develops. I will talk a bit about FarSight because that is a concept that I am very involved with. This is the FarSight array, which is once again another low frequency radio array concept for the lunar FarSight. This is a project that's been led by Jack Burns and myself, but it involves a large number of co-Is, including many who are participating in this conference. The design development has been led from JPL, and it's also been developed in partnership with Blue Origin, who really are to the Blue Moon lander, providing us with the detailed design we need to understand how that would integrate into that scale of a lander. So just to give you some background, so FarSight is a concept that's been developed as a probe class mission and was one of the probe studies that was conducted via NASA in the last few years. We worked through our overall architecture at Team X and had a number of Team X sessions at JPL to further develop our rover, base station instruments development plan. And we eventually packaged that all together into a white paper that was submitted to the Decadal Review here in the US. And we submitted our final probe study report in 2019. Now, in 2020, we began a new partnership with Blue Origin that really greatly changed the design of the project. And what I'm going to show now is just the much more up-to-date design that has improved, in my opinion, by a factor of many relative to the original design we had in our white paper. And, you know, for our design with JPL, we were very lucky because they've been very involved with Sunrise, and we had a good bit of heritage to draw on there. I'm also very involved in a project called the OVRA LWA, which actually serves as the basis for our architecture as well. Scientifically, there are two key science cases. One is neospheres and space environments of exoplanets, and of course, I'm not going to talk about that. But the other is the dark ages. And the goal really is to provide, you know, a robust measure of the global signal in the dark ages as a function of redshift, as well as providing very, very precise foreground maps to sort of, you know, begin developing a pathway towards a future power spectrum measurement as well also. Okay, I'm not going to go through the STM, which has far too much detail to elucidate on, but I want to, you know, point to it in case anyone wants to understand how the requirements for 21 centimeter actually map to an implementation for an array like this. But I am going to talk about the high level design, and the FarSight array is essentially a single mid-scale lander concept. And like I said, it's very well matched to the Blue Origin Blue Moon lander. This is sort of an overall overview of the architecture. It consists of a lander and 4 rovers. Now, in the original white paper, we only had a single rover in as our main concept. And one of the main weaknesses that had is, of course, it provides a very clear single point of failure. We have now adopted the JPL Axle rover architecture, which is much lighter and very adept for telerobotic control, and we felt was a much better choice for the FarSight concept. Each of those rovers, of course, includes a long science tether, and I'll clarify what a science tether entails. Our lander system includes, of course, all the required hardware for power, for cross-correlation of our signals, and then as well for telecoms to the gateway or to an orbiting relay. And here's just another view that shows what the lander looks like when it's deployed, when it first lands, rather. And you can see there are these 4 axle rovers that sit on top of the lander. And the first deployment is to actually take those 4 rovers and reorient them for deployment. From there, they're lowered onto the surface, and they can begin deploying the science tether. And this is what this looks like as an artist's impression. You've got 4 rovers that are winched down from their stow locations, and from there they deploy outwards, and they pull and deploy a science tether out to a maximum baseline of 10 kilometers on the lunar surface. So each of these tethers are 8.9 kilometers, and they form essentially this kind of spiral pattern and give you a maximum baseline of 10 kilometers. Now, where are the antennas? The antennas are actually embedded in those science tethers. So you actually have the rover stepping out this sort of like this kind of path you can see here as we zoom in. And what you actually have are the 2 polarizations of each antenna are embedded sequentially in the antenna. Each of those dipoles are 100 meters long and are dragged out by the rover and are deployed sequentially. And you end up with a configuration on the right where you have your antennas, not now with their electronics box for each polarization overlapping, but they sort of are meeting end to end. And the actual implication of that for our polarization has been studied by Niveda Mahesh. So how do you actually manage to get all of the electronics and the optical fiber and the actual antennas themselves all packaged? So our actual science tether is a flat ribbon that allows for easy integration into of the nodes, the electronic nodes, into that packaging that you're seeing here that sits on the rover. So this is an example of our integrated electronic nodes that actually have electronics that can function very well at very low temperature. And these are easily deployed from the AXA rover in this kind of configuration. And this shows you how that sits on top of the AXA rover. So you have this, this gives you a sense of the scale. Each AXA rover is about 2.3 meters in length. And you have the spool assembly sitting on the center of the rover, and you've got essentially a camera for telerobotics. Now, just give you a sense of what the performance looks like when you actually deploy the antenna. It gives you a point spread function that looks something like what we see here. And the key thing here is we designed this to have a good deal of redundancy. Even with the loss of a single rover after deployment, you end up with a point spread function that is pretty close to what you see here. So it's a pretty redundant configuration that can tolerate at least one rover loss in the configuration. To get to the fundamental bottom line, first, of course, the goal here is to do Dark Ages science. And we're targeting the Dark Ages trough, where you're actually targeting cosmology rather than messy astrophysics. And with a single antenna embedded in the far side array, you can get down to a detection in about 5,000 hours. Now, the potential is to use every antenna and average those down to improve your signal to noise, but really only a small number of the antennas will be highly optimized for that Dark Ages measurement. And very fundamentally, embedded in our design is the requirement to incorporate beam mapping via orbiting beacon, because just deploying those dipoles with a rover that has to avoid obstacles will give problems. And having an orbiting beacon allows you, after deployment, measure the gain pattern of every antenna in situ, and use that then to be able to allow you to back out your Dark Ages signal.
Thank you. 5 more minutes.
Sounds great. I'll be done in just a couple of minutes. So what do the data products look like? Well, obviously, we have the data product of the total power measurement from every antenna. But in terms of interferometry, we have 2 types of data product. We collect visibilities between 200 kilohertz and 40 megahertz with 1,400 channels. And we actually integrate that for 60 seconds. We don't have to worry about time smearing because, of course, the moon rotates quite slowly. And we transfer visibilities back to Earth at a data rate of about 65 gigabytes per day. That allows all-scale imaging on 60-second timescales. And we can also use M-mode analysis, as was developed by Richard Shaw for CHIME and is shown here, used for the LWA by Eastwood et al. So you can use both approaches to basically target the foregrounds rather that you want to map for future, both for your Dark Ages total power experiment in terms of characterizing the foregrounds, and also planning for a future Dark Ages experiment. Okay, one thing I've mentioned already that I want to emphasize again is that I think it's really important to be able to characterize your antenna gain pattern in situ after deployment for any experiment, be it Earth orbiting, lunar surface, far side, whatever. Because that problem does not go away when you move above the Earth's atmosphere. Now, one concept we've developed related to far side is called orb. And the idea is to actually have an orbiting beacon to map the gain pattern of every antenna. And we actually envisage maybe deploying an Earth orbiting system first for ground-based Fengquan experiments as a pathfinder. And the idea is to actually have a star tracker embedded on a small sat, and that star tracker actually changes the attitude of the beacon as it passes over the array. And why we do that is very important. When you want to measure the gain pattern of your dipole on the lunar surface or on the Earth surface, you need to know your transmission pattern of your antenna also very well, or at least control it. And the goal of the Orb spacecraft is to actually maintain your ground-based antenna or array always in the same part of the transmission pattern of the beacon to make sure you can actually map correctly the relative gain of your ground-based antenna as that beacon precesses over you and orbits over the array many times. And that is a concept we are developing in parallel to Farsight to be able to enable those those per antenna beams that are necessary basically to, I think, do cosmology from the lunar surface. Okay, some final thoughts. Clearly, the highest profile, or certainly one of the highest profile, if not the highest profile science case, to get us above the atmosphere to do radio astronomy involves 21st century cosmology, cosmic dawn, and primarily the dark ages. JWST might get us to redshift 15, but if you have no luminous matter, then you really are relying on 21 centimeter cosmology. Concepts are launching with that science case as a primary focus. And I already mentioned we already have an experiment now that's at L2 that is actually taking data. And many more in development. We're seeing CLIPS launched concepts in the next year and a half. However, I think looking at the decadal survey rather, you know, where dark ages science was highlighted so clearly, without the follow through of, you know, promoting radio, you know, space-based radio arrays, there's clearly a lot of further community engagement needed to get the message across that these array concepts are actually pretty progressed as designs, and they're no longer science fiction, as they were for Arthur C. Clarke. And my last point is, going to space only solves some problems. You still need to be able to characterize your beam, know your foregrounds, control your electronics very precisely, etc. Okay, I'll stop there and take any comments or questions.
Thank you very much, Greg, for completing also on time. Any questions, please?
Hello there. I have a question for Greg.
Yeah, Mayuri, go ahead.
Hi, Greg. Thanks for that really nice talk. I had a couple of questions about Farsight, starting with what is the plan for power? I know you did mention that there may be some solar panels, but do you expect that, you know, when the far side is kind of sees the sun, that's when you generate enough power to keep things going when you're not in line with the sun? That's the first question. And the second question is, you mentioned this type of flat cable, ribbon cable that you run along your, say, deployment of these various antennas and tethers. Does this also carry both control signals and the RF signal?
Okay, I'll answer the first question first. So in our probe study report, our original plan involved MMRTGs, nuclear power essentially, for the base station and individual PDUs for our electronics, because of course we had to keep our electronics warm, or so we thought. In the subsequent study with JPL and Blue Origins, we no longer require MMRTGs. There is technology that Blue Origin has that means we don't need that technology anymore, and I've got to be careful that I don't violate any NDAs. I think I can say that that hydrogen cells are essentially on the table, and I can't say more than that about what the scope and cost are, but what Blue Origin are developing is certainly applicable. And secondly, the electronics that are under development at JPL are such that we can actually tolerate operating at much cooler temperatures without heating those electronics, which was really exciting. Now, to your second question, there is no control electronics because our electronics are entirely passive. Now, our signals are brought so RF is brought over fiber, and that kind of, we're not digitizing at the antenna. We're bringing the RF via optical fiber, and no control is required. And this is the same principle we use for the Avro LWA here in California, and that's the basis for the design. So there is no monitor or control required. It's purely just passive measurement of the signal.
All right, thank you.
Yeah, we have one more hand raised. Chen, you can go ahead.
So maybe you mentioned, but I missed it. So does the teaser serve both as antenna and the connection, or it's the antenna is separate?
Yeah, so both the antenna and the fiber optics and the power are embedded in the same flat ribbon tether. So they're all embedded together.
So this would not affect the performance of the antenna, these other things, the fiber.
Well, the optical fiber won't, because it's not, you know, electrically conducting. Now, you know, deploying a piece of copper on the lunar surface, our game pattern is going to be complex no matter what we do. And even if there was, for example, anything in the tether that was affecting that signal, we would still have to measure in situ what that beam looks like from an Earth orbiting beacon, right? So however we deploy, whatever obstacles the rover faces, we're going to end up where our beam is not one we're going to model, but one we're going to measure. And that includes the effect of anything in our tether.
So what would be the required precision for the beam characterization?
About well, certainly sub%, depending, ultimately you need 10 to the minus 5 in the combination of the knowledge of your foregrounds and the knowledge of your beam, right? Yeah, but I'm not worried about the optical fibers which carry RF signals impacting the antenna.
Okay, thank you.
Fine. We have Raul. Please go ahead, Raul.
Okay, first of all, thank you very much for a great talk. It was really, really nice. So I have general questions and also specific questions, but because of time, I will just probably ask the general ones. The first one is, do you think that having many space concepts, especially from the same country, helps or hurts the community in general, these efforts to do 21 centimeter cosmology?
That's a really good question. And, I'm not from the 21 centimeter community, so I think I would almost ask that back in some sense. I know what I think. I think that we should build very strong consensus on what requirements are within the community, and that should be the international community. And then make sure that we communicate that very effectively to other groups in astronomy and, to NSF and to NASA and to ESA. And as to whether there are multiple concepts, there are two dimensions. There are multiple concepts in individual countries, and there are multiple concepts that are doing completely the same, trying to do the same thing. I think obviously it comes across as more credible when you've got nations collaborating on a single concept than multiple nations that are all proposing different things, because it's such an obvious thing to do to actually collaborate and do this together, that it makes it seem less credible to me if we're all trying to do it separately. Okay,
thank you very much. And quickly, the second general question: is there one minute?
Can you make it faster, please? Yes.
Okay.
Both of you.
So, is it realistic? Do the powers that be understand that this is a long-term effort and that maybe we will need a lot of iteration to get to the cosmology from space or the far side?
In my opinion, I think if you're involving budgets greater than a few million, there can be no risk, right? That's how NASA operates, and certainly I think the same applies to the countries. For low cost, you can have iteration, but not when you approach the $100 million scale. It has to work, I think, to be credible.
Okay, thank you very much.
Thank you, Gregg, for your wonderful talk. First, giving us a brief overview of the space missions and what they should do and why they're there, and your expansion on the far side. Very well done. Thank you very, very much. And thanks for a lot for keeping the time too. So I think the 15-minute break, we should take it to about 9 minutes, maybe 10 minutes. So 9:46, we can reassemble. Fine, thank you. Raul, your hand raised flag is still on. It's for something else, or it's for the same question that you asked, Greg?
Yeah, sorry about that.
No problem at all. Maybe Chen, you can share your screen so that we can at least have a nice view rather than only the panelists.
Okay.
Squares.
Wait a moment. Let me also.
Yeah, and I'll take your time. I still have a minute.
Yeah. Let me see. How do I do that? Okay.
Yes, I think it's a good time to start. Let us welcome Chen of the National Astronomical Observatories from China's Academy of Science. He's going to tell us about discovering the sky at the longest wavelength using lunar orbit array. I will give you a warning after 10 minutes. Is that fine?
Okay. Thank you.
Thank you. Yeah,
thank you for the introduction. Please. Yes. So thank you for the introduction, and I will talk about this discovering the sky at the longest wavelength, or DSL project, which is a lunar array concept. So for this audience, I guess you are all familiar with this concept of trying to probe the dark ages using the 21 centimeter line. So we could do it either using 21 centimeter tomography, where we try to map the three-dimensional structures using large interferometry arrays. Or maybe we can using a single antenna to observe the average sky temperature. And during the history of the universe, because the evolution of the spin temperature of the neutral hydrogen, we should be able to see some absorption or emission features. In fact, this is one of the predictions I made when I was a postdoc with Jordi Mirodi in 2004. So this single antenna experiment is simpler in the sense that it requires smaller amount of hardware, but actually it's also have to tackle with the strong foreground. So it's a very challenging experiment. Now, not only the foreground is very strong, if we observe from the ground, of course, we also face a number of other problems caused by, for example, the ionosphere, which could refract and absorb the electric waves when they enter the ionosphere and propagating toward the Earth. So the turbulence or the refraction of the ionosphere will couple the spatial structure in the sky intensity into the frequency structure, making it harder to measure these features in the spectrum. And on the ground, of course, at these lower frequencies, there are many radio frequency interferences, and these are reflected by the ionosphere. So it's very difficult to get a very quiet place. And finally, there's if we put the antenna on the ground, the soil is partially conducting, and with water, underground water, its reflection, its conductivity is greatly increased. So these different layers could produce reflections and standing waves, and that could generate false signals. And furthermore, if we actually looking into the lower frequencies, these absorptions by the ionosphere could be very strong. In fact, for the frequencies below 30 megahertz, we almost have a blank part of the sky electromagnetic spectrum. We have some map, but it's very poor quality. So that's the motivation for people to try to go into space, and so that to fill this blank. And So here I show the well-known HAZLAB map compared with the map made in the 1970s by the US RAE-2 satellite. So as you can see in this RAE-2 map, there's limited coverage of the sky, and also the angular resolution is not very high, so it's difficult to distinguish individual sources. But the IE-2 satellites does show that in the far side of the moon, you have a very good or nearly perfect environment for low-frequency radio observation, because there's no ionosphere, and the moon can shield the satellite from the RFI of the Earth. Indeed, I see Gregg have shown this this plot in the earlier talk, and this demonstrated the ideal environment of the far side of the moon. And of course, there have been a number of ongoing efforts to try to do this low-frequency radio astronomy from the far side of the moon. Gregg just talked about far side, and there are also this LCRT, and from Europe, there are the ARO. In China, we have also many discussions. For example, this picture provided by Professor Huilong Zheng shows one idea is to using a crater, and we have this conducting foils to produce a reflecting surface and to make a reflector. But then if you want to do the 21 centimeter tomography, the required area is quite large. This table is from a study by Koopmans et al. For the Codex mission. And so as you can see, even for a square kilometer reception area, still the signal to noise is very, very low. So in order to have some chance of reasonable success, reasonable chance for success, you probably need to start with a 10 kilometer squared mission, and maybe 100 kilometer squared effective area to actually really probe this dark age tomography measurements. So this is we hope to develop in the future, but at present probably the first step would be, first of all, to try to measure the global spectrum, and at the same time try to observe this part of the spectrum, get some rough images to at least know what the foreground look like. So here we in China have been developing this idea called the DSL for some time, and in 2014 we also collaborated with some European scientists to propose this this mission. So it is also called in Chinese Hongmeng, which means primordial universe. So the basic idea is to, instead of trying to landing on the moon, we try to observe from the orbit of the moon. Engineeringly, this is simpler because there's no need for landing and deployment, which requires a lot of technological development. And then the lunar orbit period is about 2 hours. So this can use the solar power to supply the energy, which is much simpler than dealing with the long lunar nights, which last 14 days. So we try to observe from the far side of the moon and then transmit the data back to the Earth in the front side. And this idea is that all of these satellites will be launched in a single rocket and flying on the same orbit, so that it can be accomplished in a single mission, and also the it is easy to maintain the flight formation and also to communicate with each other. So right now our concept is to have one mother satellite which is in the front. This satellite is bigger and have a high gain antenna so that they can communicate with the satellites, collect their observational data, and then communicate with the Earth. And it can also make some data processing. And we have 8 daughter satellites to make interferometry below 30 megahertz. And of course, we can also use this to observe the global spectrum, just doing single antenna measurements. So these antennas, these satellites look like this, which is basically we have a tripod on each side of the slab of this satellite. We also want to measure the cosmic dawns, so we have 1 daughter satellite dedicated to that to measure the global spectrum in the 30 to 120 megahertz frequency range. So here we use a cone-shaped antenna, and all of these will be combined into a combo looking like this and launched in a single rocket. So the interferometer array works as follows. So they all flying on the same orbit, but they have different distances. So they span different baselines, baseline lengths, so that we can probe different angular scales. And at any moment, they look nearly as a straight line, these different baselines. But as they orbiting the Earth, this baseline will sweep through the space. And for the interferometer array to work, we need to know the relative location for each satellite. That is accomplished by the mother satellite communicating with each daughter satellite using some microwave link, so that at the same time, they also serve as the synchronization and distance measurement to a precision of about 1 meter. And we also use the star sensor to take photos against the stellar background so that we can measure their angular position. So then we can determine both the distance and the angular direction of the baseline to up to 1 meter.
2 more minutes to go. Sorry.
Okay. Okay. So we, of course, the science case is to measure the global spectrum to probe the history of the cosmic dawn, and this can get rid of a lot of the systematics such as ionosphere and ground reflection. And of course, we hope to find something new. If you look at different wavelengths, you expect there's something that we do not know and will be reviewed. Here, let me show just one example. We have done this simulation. We constructed a model for the sky. This model can show how the sky at different frequencies look like. As you can see, as we drop to a lower frequency, the familiar low frequency structure changed. That's because the interstellar medium around us will absorb these radio waves, and so we can use them to probe the 3-dimensional structure around us, such as the local bubble. Okay, so there are a number of technical challenges which we have been studying in the last few years. One of them is that as the satellites are moving, so their imaging is very different from the usual ground-based array. And indeed, because the moon doesn't block half of the sky, so you actually cannot distinguish between the 2 sides of the orbital plane. So there is a mirror symmetry here. And also, as you move into different positions, the moon will block different part of the sky. So there is a positional dependent blockage. But as the orbital plane precesses, you generate 3-dimensional baselines. This solves the mirror symmetry problem. So we have demonstrated also here. First of all, we show that with the non-planar baselines, we will be able to recover the whole sky image, and also to solve this position or time-dependent blockage. We can just solve the linear equations because the visibility is linearly related to the whole sky map intensity. So we can just solve them as a mathematical problem, and that can be done. And here I also show the sensitivities. We have a reconstructed map, and as you can see, with the reasonable amount of noise, we assume there is a sky noise dominated. Then we can reconstruct the sky, and at different frequencies, we can detect the different amount of sources. Now these sources are very bright, a few hundred Jansky for the limit. But
It'll
remember,
be nice to have the conclusions so that we can have some questions.
Okay, so the low frequencies, there's of course the much more brighter. So these are the number of sources we predict with different sky models. We can detect maybe a few hundred to a few thousand sources. This is using the drones to test this working principle, and it works. We think the same can work on the satellite. And we also have done a test with the global spectrum experiment. This will, Fengquan Wu in the next talk will give this in more detail. So I just show here that we have designed a frequency independent antenna and also the receiver system to reach the required precision. So these simulations by Yuan Shi, who will also give a talk here, shows that we can recover the 21 centimeter signals. And so these are some of our field tests. And this shows that the field test results agree with the simulation, and we got some spectrum, although not yet reaching the precision of measure the cosmic dawn signal yet. So right now we have just completed our 3-year intensive study and applying for entering the engineering phase. If we are selected, we will aim for a mission launch in 2026. And we welcome international collaborations from all over the world. Thank you very much.
Thank you. Thank you for the wonderful talk and a very good overview of the entire project. Questions, please? Suman, please go ahead.
Hi. Yeah, I have one question regarding the first part of the talk where you spoke about the CODEX mission. So you mentioned that CODEX mission is particularly focusing on the dark ages signal, right? And tomography with the dark ages. So I was wondering if there are any plans to basically focus on kind of medium low frequency that is targeting the cosmic dawn and epoch of reionization. In that case, what kind of signal to noise ratio do you expect for the tomographic challenges?
Yeah, so I think this is just a study here. This is from this white paper in 2019, and as I see both in the US and in the Europe, this development are quite fluid. There's a lot of different possible concepts. So I don't know so much of whether they have also considered to probe the cosmic dawn, but I suppose that might be also part of the science case.
Okay, great, thanks.
Anyone else? Yeah, I have a small question. You showed a nice picture of how the stratification in the ground can lead to false signals or reflections. Is there been any study on what kind of problems that we may have on the moon surface? Of course, US is orbital, so it's much lesser, but on the far side, it will be much, if there is a lander, it is much more closer. Has there been any studies, I mean, in general, on the stratification of the moon's surface?
Maybe someone else could have much more knowledge. For example, Gregg may know much better than me. I haven't seen any published result on this ground reflection studies.
Yeah, even complete analysis of interferometry from the other side, from the orbits and these antennas is very impressive. I would like to go through it in greater detail.
Okay, thank you.
Yeah, let's thank him for the wonderful talk, and let's move on to the next speaker today. Yuan. She's also from National Astronomical Observatories from the Chinese Academy of Science. So, and she's going to tell us about lunar orbit measurement of cosmic dawn, 21 centimeter global spectrum. Thank you. You may kindly start. I'll give you a warning at the end of 10 minutes.
Okay, let's get started. Thanks, everyone. I'm Yuan, and I'm a third-year PhD student at National Astronomical Observatories in China. As you can see from the title, I will be talking about the 21 centimeter global spectrum measurement on the lunar orbit. It is based on the discovering the sky at the longest wavelength. We call it DSL mission, also known as Hormone mission, which means primordial universe in Chinese. Here is the outline for today's presentation. And first, I will introduce the timeline of our universe from Big Bang to today. Following recombination, we've got dark age. There's nothing but neutral hydrogen. As the time goes on, the first luminous objects ignited, which known as cosmic dawn, and then these objects continue to evolve. Eventually, full organization began to take place in universe, and then later, in time structures began to form, and then in recent history. It remains a gap in our knowledge about the cosmic history. However, because of the neutral hydrogen, the 21 centimeter signal would be a unique tracer to help us unlock the secret of the early universe. And the 21 centimeter global spectrum experiments aim to measure the sky average spectrum with high precision, so as to probe the early epochs of the universe. There is a number of such ground-based experiments, include EDGE, and they have reported the detection of absorption signal corresponding to the cosmic dawn, which is unexpectedly large as compared with predictions from the standard model that invoke a variety of mechanisms to explain the large absorption, such as extra cooling of the cosmic gas. Then many other experiments with a variety of designs are also trying to measure the global 21 centimeter signal. However, the ground-based observation of the sky at low frequencies is hindered by the ionosphere of the Earth and the radio frequency interference. So we have proposed the DSL mission in space, and Professor Xuelei Chen has introduced some basic mission concept, and it is composed of an array of satellites. Here we can see the bigger one is the mother satellite, where it will serve to collect the data from the other smaller daughter satellites and transmit the data back to the Earth with a high-gain antenna. And during the mission at the far side of the lunar orbit, most of satellites will make interferometric imaging and maps the foreground at very low frequencies. And here is one of the small satellites will make high precision global spectrum measurement to detect the monopole signal at the cosmic dawn. The data will be transmitted to the Earth at the near side part of the orbit. However, there also exists several problems, such as the orbit parameters, moon blockage, antenna response, and system noise. Then we will try to address these problems in our simulation. Here I will show,
Did we lose her voice? Or is it only me who had a problem?
It's a problem for me too.
Okay, yeah. Hi, Evan. Can you hear us? Uh-oh. Even I think her video is frozen.
I don't know, Xuelei, is there something that you could do to see her status?
I'm just trying to see if at least by chance the chat works. I'm just saying, hello, Yuan, we have lost your voice. We have lost you. Something came through. Can somebody from the same group contact her? Is it possible? Okay. Yeah, someone has offered to, Furen Deng has offered to contact her.
Right. Okay.
Still, yeah, she seems to be back. Hello. We still can't hear you. Oh, we're in the same office room, it says. She's back now. She's unmuted. That's no problem. Hello, Yuan.
Yeah. Xuelei, could you talk to us to see if you have connectivity?
I hear you. Can you hear me?
Yeah.
Yes.
Yeah.
But she's not in the same office, so.
Oh, I see. Yeah, she's looking at now. At least her video is not frozen. Can you hear us?
She's appeared. Yeah.
Maybe I transfer and waiting so that's a technical problem of it, and I can start my talk first before his simulation. Where?
Shall we go to the next talk and then come back to her when she gets her connection sorted out? Is that fine by all of you, please? Any problems?
Hello.
Hello.
She's back.
Hello.
I think she's back.
I'm back.
Okay, wonderful.
Can you
all
hear
right,
me?
carry on. Yes, we can hear you now.
Sorry.
It's okay. It sometimes happens. This is the problem of any remote connections. It can be a little bit quicker to, if possible, to compensate a little bit for your last time. Okay, please carry on. Don't worry.
Okay, let's go ahead. Here I will introduce end-to-end simulation and some models we use in this work. And here I will input the foreground model and the 21 centimeter model. And then we add the noise and some practical issues to do mock observation. And then we fit the observation data and obtain the recovered 21 centimeter signal. Here we have developed a foreground model called ORSA model, which has incorporated the free absorption effect at low frequencies and the code for this model and some relevant sky maps are publicly available. We now, here we show the generated sky maps at 30 megahertz, 60 megahertz, and 120 megahertz. And we can see here is a Gauss nebula, and the temperature is very low because of the galactic free absorption effect. And the red figure also shows the difference between the foreground global spectrum from absorption and the absorption free maps. Then we generated several models to see which model provides a better basis for subtracting foregrounds. Here we use the ORSA package to generate the foreground maps ranging from 60 to 120 megahertz. The 5 terms log polynomial sky model can fit well in all cases, and we take it as our fiduciary model to subtract foreground. Then we consider the 21 centimeter signal models. First, the 21 centimeter model is reported by the H experiment. And the second is a simple Gaussian model with 3 parameters. The red figure shows the 21 centimeter signal for different cases. The first case in the gray dashed line describes the describes that there is no 21 centimeter global signal to be detected. And the second case shows 21 centimeter of edges detection in the blue solid line. And the third and fourth cases describe the evolution of 21 centimeter of Gaussian model. And here the A represents different amplitudes. Next time I will show some orbit parameters. We shall consider a nearly circular orbit for the array of satellites. In choosing the orbit parameters, we keep in mind 3 aspects of the problem. First is the stability. The next is the good observation time during which the Earth and the Sun is shaded. And the last is about the nodal precision of the orbit, which generate a 3-dimensional distribution of baselines, which is very important in interferometric observation. Here we show, in this table, we show the fraction of good observation time for 300 kilometer orbits with different inclination angles during 5 years. In this observation, we will choose a 300 kilometer circular orbit with an inclination of 30 degrees. The basic parameters of the simulation are listed in the table. In this work, we consider several antenna cases. In the first case, we consider a disc cone antenna with very small diameter disc. Here, the diameter is about 55 centimeter, which has a nearly frequency independent beam profile. Here, we show the beam gain profile and the frequency gradient. Next, and as an example of frequency-dependent beam, we consider a disc cone antenna with a large disc. The diameter is 300 centimeter. Then we can see, here we can see a significant variation of the beam profile with the frequency. And we can see a small side lobe appears at the 120 megahertz. And then here is the frequency gradient of the large diameter disc. Then we also plot the residues for these two antenna cases. We can see the residue for the large disk is significantly higher than that of the small diameter disk. For the small antenna, the frequency-dependent beam could be filtered out with our foreground model. However, the frequency-dependent beam cannot be removed, so we should take care of this condition. And then
is it possible to conclude so that we can have a couple of questions at least?
Okay.
Try to conclude as soon as possible. It's okay. A minute.
Okay. Then we add the noise in this simulation and fit the foreground and 21 centimeter signal with edge 21 centimeter model and a Gaussian model. Here we show some results, and first we observe at different positions. We can see the here first we show the beam seen from the different positions at one orbit, and the shape of beam depends on the position of the satellite on the orbit. And then we show the observed foreground spectra at different positions, and then fit the signal with the foreground model. We found the beam-weighted signal can be reconstructed with a high accuracy. The four segments yield similar residues, and the residues are all very small. Then we consider a foreground-only model, and we generated the sky maps and with free absorption effect. The mock observation include all practical issues, and here we show the difference between the antenna temperature and the recovered sky temperature after fitting and removing the foreground. The noise level corresponds to the 10 orbits observation, and the red figure shows the best fit parameters of the foreground. Okay, in this work, we focus on whether the 21 centimeter signal can be detected by the satellite orbiting the moon. And here we plot the observed signals after the 10 orbits observation. We can see the 21 centimeter signal can be reconstructed very well in this simulation. Here is my conclusion. We provide the first simulation of the upcoming lunar orbit survey by end-to-end simulation, and we find that high sensitivity can be obtained despite some practical issues exist. Here is some reference of the HOMO or DSL mission. Okay, that's all from me. Thank you.
Thank you very much for the talk. Sorry that we lost you for a couple of minutes. One quick question. Is anyone? Hi, Mayuri, go ahead.
Hi, Yuan. Thanks for that talk. My question was, what is the requirement of the RFI shielding of all the electronics that sits near the antenna? What is the requirement you expect?
She's perhaps talking about the emission from the electronics being caught up by the antenna.
Yes. Sorry, can you repeat the question?
So in our hardware part, so we require our RFI shielding, I think more than 120 dB. I think now that's the requirement, more than 100. Yeah.
Okay. And maybe I'll follow up later offline. Thank you.
Okay, thank you.
Yeah, let's thank Yuan once more for the wonderful talk. I'm sure people can catch up with you, during coffee break or offline. Yeah, then we have the last but one talk for the day. That is by Fengquan Wu, once again from the National Astronomical Observatory, Beijing, China, measuring 21 centimeter global spectrum of the lunar orbit and its ground testing. Okay, so yes,
thank
Frank,
you very much. It's such a pleasure and honor to have Chen to join this meeting. And I will met our screen. Could you see my screen?
Yes, very much, very clear.
Okay, that's great. Okay, I remove this one, and then okay. The last two talks by the Professor Xuelei and the Yuan have very good summarize on these hormone projects. I only focus on this hardware on this 21 centimeter global spectrum measurement. So the great Gregg have mentioned this. So this is now will not be the first scientific payloads in the space in China. So the Gregg have mentioned this the payload, scientific payloads in the relays satellites. Actually, we have another two. One is on the lander, another is on the Longjiang orbit satellite. So we have participants on this project for a couple of years. So this is we have two satellites launching into the lunar orbits, but unfortunately we lose one in the transfer orbit. So we only have one. By this one, we get some data, and from these data, this is the frequencies and this is time. You can see when the satellite goes into the back of the moon. You can see it's quite convenient. This is show why we need to go to the far side of the moon in the lunar orbit to measure the spectrum. And Xuelei have mentioned this hormone project. Basically, there were two scientific objectives. One is for the whole sky image. Another one is this global spectrum. The spectrum we want to measure is from the 30 to the 120 megahertz. So you can see that the rich structure can reveal the evolution of history, the universe. There was more than 1,000 of all kinds of theoretical prediction, but we know that on the experiments side, there was on the space. So from the 1960s, there was very few results, and all these results are not consistent. So I know that almost from the 20 years before, a couple of teams dedicate their great effort on developing all kinds of different instruments to try to measure these signals until we know the 2016 that the Edge is published that the stunning results on this absorption.
Hello, can you hear me?
Hi, Raul, yes.
Yes, so same problem again, unfortunately.
Yeah, same problem again. View. Uh-oh. Yuan, can you hear us? Can you call him? Is it possible to get in touch with him? One of you? We lost him altogether, but he will come. That's a good sign in a sense that he has recognized that we are not hearing him. So same problem.
He's back. I'm gonna promote him to panelist.
Yes. Oh, thank you. We'd lost you for a couple of minutes. Can you hear us, Wu? No, we still don't have his video or the audio.
Maybe he can try to switch off his video and to save the bandwidth. Maybe.
Yeah, we can recommend that. I'll do that. We lost him again. Plays out.
I guess it starts to become a possibility to ask Mayuri to go now.
Mayuri, is that fine? Can you do that?
No problem.
He's back again. He's back again, actually. Let's try it one last time.
Okay, fine. I don't see him. Oh, you have to let him into as a panelist. Okay. Yes.
Now, could you hear me?
Yes, it's nicer if you can switch off your video and keep the audio alone on. Maybe we will have you continuously.
Yeah, sorry. I think we should update our network. Yeah. Could you see my screen?
Yes, we can see.
Okay, that's great. So,
full screen, you will have to go. Slideshow.
Yeah, full screen. Okay. So, very sorry. So I must say, this was 21 centimeter worth is quite challenging. So I go quickly. So now the more popular design we know that's use the wide beam antenna, use the DG switch to do the calibration as frequently as possible, and the two typical designs like the edge and there. So, but this kind of the antenna is 2 meter long, and for our this is the stored configuration or antenna array. So you can see that's only 2 meter. Something like 2 meter long and 1.5 ton, and so small antenna array we cannot use this large antenna. So this is something we consider in our antenna design. So we want to have a commuticity of the antenna. We need to have very smooth response, and we won't have a wide beam. Also the side and way as another consider. So after we have working on a lot of the different kind of antenna, eventually we think that at least the 2 types of these things could satisfy our requirement. One is this discon antenna only 30 meter high. Another one is the small wing antenna and less than 40 centimeter long. And another thing is that we can include the matching network and could improve the matching between the antenna and the receiver. That's but this part is ongoing work. So we didn't include in the testing below. And this is our system. So we have this VNA module on board, and we have this calibration subsystem, and we have this RF switch matrix allow the VNA to do the calibration, also to measure the antenna and measure the receiver channel. So this is the antenna design. You can see that the antenna is quite small. The height is smaller than 30 centimeter. And we measure our antennas in the chamber room, microwave chamber room. So you can see that the S11 of the antenna is quite small, and this is the beam pattern. We measure the beam pattern in this chamber room, and we compare it with the simulation. You see, it seems quite well. This is different. The hardware board we developed. This is the VNA board, and And this is the prototype we built for the field testing. And we select a quite good size on the east west or northwest of China. Over there, not too far away, the antenna array. So we were working on working on this whole sky survey, also to have multi-beam system. Over there, we put these prototypes on the ground, just on the ground for testing. And the first thing you can show you that I showed this here is the temperature variation. They have a thermostatic system inside, and you can see there's outside the temperature variation is more than, I think, 20 Celsius. But in
to conclude in the next 3 minutes or so that we can have a couple of questions too.
Okay.
Yeah, thank you. Sorry for the trouble. Go ahead.
Okay. So the temperature variation is less than something 0.2 Celsius for the 1 day, hold 1 day. And this is at one parameter measured by the VNA inside the system. You can see this is quite small, and this receiver is less than minus 20s. So this is the, we plot here the water flow, or this is the time, YSC, and this XSC is frequency. We can monitor the variation. I think it's quite stable for a couple of days. We use the temperature variation load for the absolute calibration, and this we can heat the load to the very high temperature about around 160, and then decrease the temperature. And for this one cycle, we can get the equivalence temperature of the noise source, and this is around 2500. Now this. And if we use the more cycle to do this, and we almost get the consistent result. We also can estimate the system temperature using some equivalent method, and we get the temperature, system temperature is around 100 Kelvin at this level. This is what we do the observation. So the pink color is the real measurement, and the blue color is the simulation. So this is 2-day data. This P is when the galaxy is on the beam, and that's when the galaxy is off the beam. So we can see the variation, but this result I see is quite consistent compared. So when we consider that the simulation cannot have a very high precision. This is the sky spectrum we get at the moment. So this is also the low sky, the quiet sky when the galaxy over the beam, and this is the average. If you go back to this image, you can see that's a little bit far away. There was another antenna. Where we have one student. She was very interested in the edges, the antennas. She made a little bit improvement in the chromaticity, and he also measure the sensing, the sky spectrum. Also got the 3-day data. You can see that the temperature, the sky temperature vary with the time, and quite is consistent with the simulation. Also, so we hope after a few years of development, we could have this kind of the satellite or put in front of this antenna arrays, and so how this can break through the vastness of this measurement. And okay, so I think I should thank a lot of people gives us valuable help during this development. Thank you very much. That's all.
Thank you for this wonderful talk. We wish we had a little bit more of details from you about the testing. Any questions?
I have a quick question.
Please, Raul. Yes.
You talk about VNA being part of your instrument. Is that a custom design, a custom VNA that you built, or is that a commercial one?
We have two different kind of. The one is the commercial one. Another one is by the we make one. So that's these two is there was a difference is about 0.0 something like 0.2, 0.3, or something like this at this level. So we do development we cooperate with other institutes to develop the ones using in the payload. That could be, yes, a very precise one. This is ongoing work. Yeah.
Okay, thank you very much.
Any question in the Slack? I can just check once. Just give me a moment. No, I don't see any question. So let's thank you. Thank you very much for that really detailed, real detailed testing that you guys have carried out. It's very impressive. It will be nice to talk to each other sometime later. Yeah.
Thank you very much.
Then we are now on to the last session, last talk by Mayuri. Kindly share your screen, and you're going to talk on PRATUSH.
Hi, are you able to see my screen?
Yes, very clear.
Great. Hi, everyone. I'll be presenting a work on PRATUSH. PRATUSH is the Indian proposed space mission, which will be a custom designed lunar orbiter to detect the 21 centimeter signal from cosmic dawn and epoch of reionization. All the work I'll be presenting here today has been carried out at the Raman Research Institute. So given that this is a specialized audience, I don't think I need to convince you about the importance of detecting the signal itself and the various challenges that face the signal detection. But I'll quickly summarize again some of these challenges to set the stage for some of the design choices we have undertaken for PRATUSH. The speakers have gone before me have kind of given a somewhat detailed overview of each of these challenges, so I'll try to keep it quick. So most standard 21 centimeter global signal detection experiments have a few parts or subsystems, as I'll call them, starting with an antenna, which is connected to receivers that contain RF electronics. And this analog signal or RF signal is digitized in some digital receiver. And then this is analyzed using various data analysis method to detect the signal. So I've highlighted here different challenges facing signal detection in blue and pink. The pink challenges face any experiment irrespective of maybe where it operates. That is, whether it operates in space or whether it operates on Earth. We always have to pay attention to the kind of antenna properties that you're working with, any reflections or standing waves internal to your receiver that can confuse the signal detection, dynamic range limitations, self-generated RFI, as well as the very methods you use to separate foregrounds from the signal. And specific to ground-based experiments, there are a few challenges that several speakers have highlighted, starting with ionospheric effects. This can be in the form of refraction, absorption, emission. And of course, this is frequency dependent, and the effects are somewhat stronger towards the lower frequencies for this cosmic dawn and epoch of reionization signs. But nonetheless, it is important to factor in that there will always be some kind of question in confidence of any detection given ionospheric effects for a ground-based experiment. Now, for this, the motivation is that you want to go to space. So basically, you want to be off the surface of the Earth, and you want to go to space. Now, the question that we ask is where in space, and that's been well motivated by previous experiments and simulations, is that you want to operate in a region that is very radio quiet, and the far side of the moon provides such an environment. And from recent simulations that also Gregg presented, we find that up to 80 dB of suppression of terrestrial RFI can be expected in the lunar far side, depending upon various orbital and frequency parameters. So now the question begins, we ask the question, okay, you want to go observe in the lunar far side. So do you want to observe as a lander, or do you want to observe as an orbiter? And here we have taken the design choice that we want to be a lunar orbiter. Again, because of one of the challenges that faces ground-based experiments, which is when you place an antenna over any medium, such as Earth, there is this issue of stratification of the soil properties as a function of depth. And to the extent or the sensitivity that one would look for this signal, you might very quickly start seeing the effects of coupling to the Earth beneath the antenna, including various edge effects of any ground plane losses, and just by virtue of operating in an inhomogeneous medium. So from this, we have decided that PRATUSH will be a lunar orbiter experiment. And that brings me to what PRATUSH is. PRATUSH stands for Probing Reionization of the Universe Using Signal from Hydrogen. Yes, it's an acronym, but it's also a play on the word PRATUSH, which in Sanskrit and various Indic languages also mean dawn and sun. So it's quite fitting for such an experiment. In the overall plan, PRATUSH will operate from 40 to 200 megahertz and target the detection of both the signal from cosmic dawn and reionization. Today, I'll be presenting the baseline design, which is explicitly focusing on the signal from cosmic dawn, and this will operate from 55 to 110 megahertz. And like I mentioned before, this experiment will be custom designed primarily for the science goal of detecting the signal from cosmic dawn and EOR, cosmic dawn in the baseline design case. And all the design choices that we are making in our subsystems as well as receiver all ensure that it will be an experiment that will make a high confidence detection of the signal. I'd like to mention here that PRATUSH comes from the same group that runs the experiment SARAS that has been shown in several slides before. So we have a lot of expertise on building sensitive radiometers that operate on the ground. And very recently, we had a result from SARAS-3 that rejected the EDGIS signal detection, claiming that it's of cosmological origin, to about 95% confidence. And I'd like to point everyone to Saurabh Singh's talk, which was in a session a couple of days ago. I'm happy to report that just after about 2 years in a seed funding pre-project study phase, PRATUSH has been recommended by a committee appointed by the Indian Space Research Organization, or ISRO, to move to project mode. So we will be seeking to actively apply to become a ISRO project. All right, very quickly, I'll summarize the design philosophy of PRATUSH. Oh, sorry about this extraneous dashed line at around 65 megahertz. Well, so that plot on the right shows you the window of 55 to 110 megahertz where PRATUSH will operate. And given the spectrally rich nature of the signal that we are trying to detect, as has been the philosophy with SARAS, PRATUSH will continue to adopt the same philosophy of having all the elements of the telescope to be very smooth in its frequency properties. Hence, we don't want to introduce and correct in retrospect any features. Of course, there are tolerances that we will be simulating to place numbers on the level of smoothness of the various subsystems. But that is the overall design philosophy of the instrument, so antenna and the receiver design. I'd like to point out here that we have taken the approach that the PRATUSH antenna sits right on top of the spacecraft. So all the electronics, including the PRATUSH electronics, analog and digital, as well as the satellite electronics, are enclosed beneath the antenna. This will pose a few challenges, as I'll mention later, but we decided to tackle those challenges head on, and I'll come to that quickly. And PRATUSH will make scientific observations when in the shadow region on the lunar's far side, shadow of the Earth and the Sun. And it will have solar panels that will charge batteries when in view of the Sun, and data will be downlinked to Earth when in view of the Earth. And like I mentioned, all subsystems are individually designed to be maximally smooth. So here is the PRATUSH baseline design concept. Like I mentioned, that the antenna itself somewhat enshrines the bus or the spacecraft structure beneath it, and the payload or the PRATUSH analog electronics, the digital electronics, as well as spacecraft electronics are all enclosed right beneath this antenna. The antenna we have designed is a monopole antenna. So it is a monocone over a profile reflector, and I'll come to what determines the design choice of this specific type of antenna and what its properties are shortly. So here I'd like to mention one of these challenges that I mentioned in the previous slide, which is several ground-based experiments separate the antenna and some analog receiver electronics from the digital receiver electronics by either running a coaxial cable or a fiber cable to separate somewhat noisy electronics such as clock lines in the digital receiver. And there is some more freedom in the amount of EMI shielding that your enclosure needs to provide. However, for practical reasons, this is not quite possible in space, or at least to a very limited capacity. Hence, we decided to tackle this challenge of EMI shielding head on and place everything that we think will generate some noise right beneath the antenna, and with the antenna reflector also kind of acting like a shield in itself, in addition to the various EMI shielding strategies that the receiver will employ. And the sides of this bus will have solar panels. And even though it's shown as a solid object, this reflector will be made of either a mesh or spokes of wires, which will allow optical light to irradiate the solar panels, whereas it provides a continuous surface for the RF frequency of operation. So let me come to the PRATUSH antenna. Like I mentioned, this is the design that we have gone with, which is a cone over a profile reflector. And the reason why we have arrived at this design is because from ground-based experience with SARAS, we have as a group decided to primarily focus on monocone antennas, given that sometimes the balun which connects the dipole antenna to receiver electronics can have frequency dependent structures that are hard to calibrate. In addition to this, you might notice that given that a metallic structure like the spacecraft or the bus is sitting right beneath the antenna, any change in the properties of this bus also non-trivially affects the shape of this antenna. And we have an antenna validation pipeline where every time we have iterated over the antenna design, be it with a change in the bus dimension or with the antenna properties itself, we generate antenna parameters such as the beam as a function of frequency as well as return loss. And instead of individually qualifying or placing smoothness restrictions on the beam or the antenna S11, we let the antenna pipeline, validation pipeline, do the job for us. So to this antenna, which has these properties listed on the left, we've put in an input sky model, which is physically motivated. We also factor in the presence of the moon beneath at a certain distance. So in the far field of the beam, you will still catch some emission from the moon. And this antenna, given that it has some response as a function of frequency, given the beam as well as the S11, you get a final antenna response.
Mayuri, maybe 2 more minutes. Will you be able to wrap up? Thanks.
Sure, yeah. And we do a signal detection confidence test on a various range of signal models as listed below in the antenna frame of reference. And we have found that for this design, for a kind of fiducial model of the global 21 centimeter signal from cosmic dawn, we are at RMS residuals of below 10 millikelvin. And that's, we find, is a satisfactory number. So I'll quickly move on to the analog receiver of PRATUSH. This has a very similar calibration scheme for the bandpass as SARAS-3, which is on the right panel of that architecture diagram. And on the left panel, we have also included a custom VNA section, which will, in addition to our simulations on the ground, help us do a coarse measurement of the antenna S11 in space in situ. Finally, the digital receiver is once again motivated by the design adopted in SARAS-3. However, we will be using higher technology readiness level components and some extra processing on the satellite to reduce the data rates to a manageable number for downlinking. And this is the current status of PRATUSH. We have a lab model or a concept model hardware ready. We have already individually qualified and tested various subsystems of this experiment. And shortly, we will be going to the field for a full integration testing of this experiment on Earth. And we have an expectation of what this antenna would see on Earth, and hence match it back to what it would look like when operating in space. And I'd like to point out here that our current biggest R&D challenge is the EMI shielding of electronics. Given that any traditional methods of EMI shielding, such as a stainless steel enclosure, also makes the payload quite heavy. So we are exploring novel materials as well as paying attention to the EMI shielding of individual cards and components, as well as choice of clock frequencies and so on. And we are working closely with the Indian Space Research Organization, who have formed a technical advisory team to kind of revisit and refine our design with their inputs. And subject to approval, we will move from the lab model to the engineering model and finally the flight model. So I'd like to end with a slide of all the people who have been involved in this effort, and I'll take any questions.
Thank you, Mayuri, for keeping up the time. Any questions?
Hello, thank you for a very nice talk. So where do you see the solar panels will be placed? The solar cells will be placed?
Sure. So the batteries themselves will sit inside this bus structure, even though it's not explicitly pointed out. But you can imagine that if this is a cube or a cuboid, the side faces of this cube will be lined with solar panels.
The side faces, but then I see.
Yes. So we
So
know
it looks from. Sorry.
Go ahead.
So from the figure you show, it seems a very small side view, for installing. Yeah.
Sure. Yeah. So I want to point out that this blue box here extends all the way to this top, and it's even though this I don't know. Can you see my mouse pointer?
Yes.
Yes, we can.
Yeah, so this gray reflector, even though it looks as a solid object and opaque, in practice, it will not be opaque. For example, in a somewhat an illustrative example here is the ground model, where you have a mesh, but we would ideally go for something like spokes of wires, so that a lot more of the side panel is exposed. But of course, we will have to factor in any shadowing effects and how that affects the efficiency of power.
Okay, yeah, thank you.
I have a couple of questions.
Yes,
Sure.
go ahead, Raul.
Okay, very nice talk. Congratulations on your progress. When and where do you intend to do the preliminary measurements? That's the first question.
Right. So to start off with, initially we have a test facility about 80 kilometers from Raman Research Institute called Gauri Bidnoor. We will be going there, but we will have to do some heavy filtering of RFI, from the 88 megahertz and above, which significantly reduces our effective operating band. But once we are confident with our various other initial tests, we'll probably go out to a further radio quiet location somewhere in India, potentially.
And what's the timeline?
So we anticipate that this full system testing at Gauri Bidnoor, the first phase, will happen in about a month's time. And depending upon how progress goes from those measurements, we'll have a better idea for the next phase.
Okay, and quickly, my second question. What is the expected power consumption of your satellite? And also, how will you manage temperature of the electronics, and how will you compensate for expected drifts?
Sure. Okay, that's a great question. Right now, we have two sets of numbers for power. Purely using ground-based components, we expect the power of our receiver alone is 200 watts, but that's not the number that we will be flying with. We have done the calculation for what the equivalent space qualified parts consumption would be, and after a lot of optimization for power, and that number comes out to be about 25 watts, and that's our electronics alone. And sorry, can you repeat your second question?
Temperature range and compensation.
Right. So for the electronics themselves, we have assumed that the box that is shown beneath is of standard CubeSat dimension. So there will be some thermal regulation of all the electronics beneath the antenna, and that will be thermally regulated. And we are working again with ISRO on this. As far as the antenna itself is concerned, we are very aware that there will be that will be the most exposed element environmentally, and any changes in the mechanical properties due to heating and cooling will change antenna properties to extent that we'll care about. So in addition to simulations, we will also explore options of baffling with ISRO. But again, I keep reiterating here that any change to the overall structure around the antenna or beneath the antenna will end up changing the antenna design a bit to continue to validate, pass our validation pipeline.
Thank you very much.
Any other questions? Well, thank you, Mayuri, for that wonderful lightning talk at the end of the day and the end of the sessions, all the sessions. I'd like to take this opportunity to thank all of you speakers. I'm very delighted to hear what happens when you have a lander, what happens for an orbiter, and also reminding each other rather, saying that, look, just because we have avoided the ionosphere and the man-made RFI, we still have lots of challenges required, and they're not over, and we have to take care of that. I think I would like to thank all the speakers for enlightening on several of these concepts. Thank you very, very much. I think Raul has something to say on behalf of the organizers on himself. Please, Raul, it's over to you.
Thank you very much. Well, first of all, I would like to thank the speakers again of the session, and I want to thank you, Uday, for sharing the session. It was really nice beyond some technical difficulties, but that is still part of the job. So thank you all very much. And on behalf of the organizing committee, I would like to thank all the speakers, session chairs, and attendees of this SAZERAC 21 centimeter conference. In my opinion, it was great. It was very successful on every front. And well, it hasn't really ended. Please continue the discussions on Slack and watch the YouTube recordings to absorb all the details and good information. And with that, again, I would like to thank you all and wish you all the best. And we will see each other again next time. Thank you very much. Bye-bye.
Bye. Thank you.
Thank you.
Thanks all.